In a previous video, we looked at exponential growth and decay. That was just standard exponential growth and decay. There are a couple other types of growth and decay that are special and have some special formulas. The first one is compound. Compound is for when the percentage or the change happens more than just once a year. It's compounded several times over the year. However, the percentage is still just for a year. A compound equation is y equals a times 1 plus or minus, usually it's plus though, r over n to the nt. So let's figure out what each of these things means. A is still your initial amount. R stands for your annual percentage rate. That's a percentage. N stands for the number of times it gets compounded. Ditto for that N. And last is time in years. So we're going to use that equation when we talk about some compound growth and decay situations. The second one is continuous. Continuous growth or decay has to do with the natural base. Continuous growth or decay uses the equation y equals a e to the rt. E is that natural base. A stands for the initial amount. R stands for the percentage rate. I keep doing that on my percent, sorry. And T stands for the time in years. If the percentage rate, if R is greater than 0, it's growth. If R is less than 0, it's decay because it's getting subtracted. That rate is getting subtracted. Now, you're going to see a lot of the versions of these two formulas all over the place, especially the second one. One thing you might see is you might see an equation that has a P, E, R, T. It's the same thing. P, A still stands for the initial amount. So we're going to use these two equations to help us look at some compound and continuous growth and decay situations. So here we have a customer who purchases a TV for $800. What a steal. Using a credit card. The interest is charged on the unpaid balance at a rate of 18% per year, compounded monthly. This customer makes no payments for 1 year. How much is owed at the end of the year? So this is a compound problem, which means we need to use our compound formula. We have the initial amount, we have the percentage rate, and we have the compound, the number of compounds. It's monthly. That means it's compounded once every month. So think about how many months are in a year. There's 12. So when we plug everything into our equation, we're going to end up with 800 times 1 plus 0.18 divided by 12 to the 12 times the number of years, which is 1. There are a lot of online calculators as well as handheld calculators that will allow you to type the equation in exactly like that, and then it will pop out the answer for you. This is probably the way you want to go so that you do not make any rounding errors, because exponentials change very, very quickly. Rounding too early will get your answer off too much. So if we type that into our calculator, we're going to get our result for how much we owe for the TV at the end of the year. And in this case, it's $956.49. So your computer's currently worth about $189.96. Your computer values decreased by 43% each year. How much did you pay for the computer 3 years ago? Is this a compound or continuous problem? It's actually not, because you do not see those terms compounded, monthly, compounded, whatever, or continuously compounded. Because you don't see that, we just use our standard equation. Y equals AB to the X. So let's go ahead and try to recall how to use that. My computer is currently worth $189.96, and I want to go back in time to find out how much it was worth before. So we're going to do 189.96 times. So it's getting decreased by 43%. So 1 minus 0.43 to the time. Since we're going back in time, time is negative. So to the negative 3. We're going to use our good calculator that allows us to type that in just like that. And we should figure out what our computer was worth about 3 years ago. Type that in. You should end up with $1,025.74. So this one wasn't an example of compound or continuous. I wanted to throw it in there so you could see that those situations are different. You have to keep that in mind when you're deciding which formula am I going to use. The half-life of carbon-14 is 5,730 years. If a sample originally had 500 grams of carbon, how much would be left after 9,000 years? This half-life is actually a continuously compounding problem. When we do a half-life, we use our equation with E as the base. So just to recall, the equation is y equals a times e to the RT. So initially we have 500 grams of carbon. We can write that in. Times e to the rate. Now this is a half-life, which means it's getting cut in half every time. So the rate is negative 0.5, or negative 50%, times the number of times that it has its half-life. So we have 9,000 years, and it's going to go through a half-life. Well, the half-life is 5,730 years. So what do we need to do in order to find out how many times it goes through that half-life? We need to divide. So it would be to the 9,000 divided by 5,730. That will tell us how many times it actually goes through a half-life. But if we have a good calculator, we can type our equation in just like this, and that'll pop out the right answer for us. Because we're dealing with e and that nasty fraction in the exponent, we don't want to try rounding too early so that we don't carry over any mistakes. So make sure you have one of those calculators available. Type that in like it's supposed to look. And we should figure out that after 9,000 years, we will have about 227.98 grams. So you deposit $2,000 in an account that earns 5% annual interest. We want to find the balance after 2 years if the interest is compounded annually, quarterly, monthly, and continuously. So we're going to have to write 4 different equations, and let's figure out what is the best deal. What kind of account should I use? Compounding just once a year, compounding continuously. So we're going to start out with our just standard exponential equation because we're going to do annually. That means we don't have to divide. Or you can use the compounded equation. Either way, you're going to have 2,000 times 1 plus, if we use the compound equation, 0.05 divided by 1, because it's compounded just once, to the 1 times 2. So you can see why it wouldn't matter if you used our standard equation or if you used the compounded one. The dividing by 1 isn't going to make a difference. Alright, so that's going to give me my solution if I compound annually. So again, using our good calculator online or in your hand, we're going to type that in. And it looks like we're going to have about $2,205 after 2 years. Not bad. Now let's think about the next one, quarterly. So that means we're compounding 4 times a year. So we have 2,000 times 1 plus 0.05 divided by 4 to the 4 times 2, because it's compounded 4 times every year times 2 years. When we evaluate this one using our good calculator, we get about $2,208.97. So, it looks like we're doing a little bit better for ourselves. The next one is monthly. So that means 12 times a year. Start out with 2,000 times 1 plus 0.05 divided by 12 this time to the 12 times 2. Again, using our good calculator, type all that in. We end up with $2,209.88. So, even better. Now let's see what happens when we compound continuously. Remember, the continuous formula is the one that uses e as our base, and our percentage rate goes up in the up in the exponent. So we have our beginning amount, 2,000, e to the rate, 0.05, times time, or how many times it was compounded. It's 2 years, so that's going to be 2. Use our fancy calculator, and we are going to end up with $2,210.34. So obviously, our best option is continuously. Not all savings accounts have that option, though, but I want you to keep that in mind should you decide to open an account sometime soon. Or not so soon, but next time you open an account, think about the compounding that they offer. It's one thing to offer 5% annual interest, but it really makes a difference when you talk about whether it's an annual thing or whether it's compounded continuously. So here we have one last half-life problem. Cobalt-60 has a half-life of 5.3 years. And if a pellet has been in storage for 26.5 years and it contains 14.5 grams of cobalt-60 right now, how much of this radioisotope was present when the pellet was put in storage? We're going back in time. What does that tell us about our time in our exponential problem? Time is going to be negative. So this is a half-life, which is a continuous natural relationship. So we're going to use our continuous equation. 14.5 is what we know right now. There's e to the negative 0.5, because this is a half-life problem. The rate is going down 50%, so it's negative 0.5. Times time. Now here's where it gets a little bit tricky. A half-life is 5.3 years, and we have 26.5 years to do it. So to figure out how many half-lives it goes through, we have to divide. Means we're going to have 26.5 divided by 5.3. The other thing we need to remember is we're going back in time 26.5 years. So we need to use a negative sign. Now in our calculator, we can go ahead and type that in exactly how it is if you're using one of those calculators I've linked to. And you end up with 176.65 grams. So let's think about this. This is what we had when it was put... this is what we had in the initial time. Then 26.5 years later, we only had 14.5 grams left. So does it make sense that we have more, that this is a bigger number? Yes, because that's how much it started with. And this was a backwards problem. We were going backwards. So just to do a little recap for us, we have a couple special types of exponential problems. All exponentials follow the same basic form, y equals ab to the x. However, when we have compound, interest, and when we have continuous change, we have a couple of special equations that we need to think about. So remember, for our compound problems, usually compound interest, we have y equals a times 1 plus the rate, the percentage rate, over the number of compounds to the number of compounds times time. When we have continuous, that's where we need to think about our natural base. So we have y equals a times e to the RT. Remember, When r is less than 0, that means it's decay. It's going down, or taking away a rate. When r is greater than 0, it's growth, because we're adding on a rate. This is what we use for half-life problems, for natural half-life problems, because a half-life has a rate of negative 0.5. And since half-lives occur in nature, they're occurring all the time, continuously, and that's why we would use a continuous formula for that. So this was just sort of a recap of our extension of exponential problems.